A screw thread, or often shortened to thread, is a helical structure used to convert between rotational and linear movement of force. A screw thread is a ridge wrapped around a cylinder or cone in the form of a helix, with the former being called a straight thread and the latter called a tapered thread. A screw thread is the essential feature of the screw as a simple machine and also as a fastener. The mechanical advantage of a screw thread depends on its lead, which is the linear distance the screw travels in one revolution. In most applications, a lead of a screw thread is chosen so that friction is sufficient to prevent linear motion being converted to rotary. That is, so the screw does not slip even when linear force is applied, so long as no external rotational force is present. This characteristic is essential to the vast majority of its uses. The tightening of a fastener's screw thread is comparable to driving a wedge into a gap until it sticks fast through friction and slight plastic deformation. Applications. Screw threads have several applications: fastening fasteners such as wood screws, machine screws, nuts and bolts, connecting threaded pipes and hoses to each other and to caps and fixtures, gear reduction via worm drives, moving objects linearly by converting rotary motion to linear motion as in the lead screw of a jack, measuring by correlating linear motion to rotary motion as in a micrometer, both moving objects linearly and simultaneously measuring the movement, combining the two aforementioned functions, as in a lead screw of a lathe. In all of these applications, the screw thread has two main functions. It converts rotary motion into linear motion. It prevents linear motion without the corresponding rotation. Design. Gender. Every matched pair of threads, external and internal, can be described as male and female. For example, a screw has male threads, while its matching hole has female threads. This property is called gender-handedness. The helix of a thread can twist in two possible directions, which is known as handedness. Most threads are oriented so that the threaded item, when seen from a point of view on the axis through the center of the helix, moves away from the viewer when it is turned in a clockwise direction, and moves towards the viewer when it is turned counterclockwise. This is known as a right-handed thread, because it follows the right-hand grip rule. Threads oriented in the opposite direction are known as left-handed. By common convention, right-handedness is the default handedness for screw threads. Therefore, most threaded parts and fasteners have right-handed threads. Left-handed thread applications include where the rotation of a shaft would cause a conventional right-handed nut to loosen rather than to tighten due to fretting-induced precession. Examples include the left-hand pedal on a bicycle, the left-hand grinding wheel on a bench grinder, the lug nuts on the left side of some automobiles, the securing nut on some circular saw blades. The large torque at start-up should tend to tighten the nut, in combination with right-hand threads in turnbuckles and clamping studs, in some gas supply connections to prevent dangerous misconnections. For example, in gas welding, the flammable gas supply uses left-handed threads. In a situation where neither threaded pipe end can be rotated to tighten, loosen the joint, e.g., in traditional heating pipes running through multiple rooms in a building. In such a case, the coupling will have one right-handed and one left-handed thread. In some instances, for example early ballpoint pens, to provide a secret method of disassembly. In mechanisms that give a more intuitive action, as the lead screw of the cross-slide of a lathe to cause the cross-slide to move away from the operator when the lead screw is turned clockwise. The depth of cut screw of a Stanley-type metal plane for the blade to move in the direction of a regulating right-hand finger. Some Edison base lamps and fittings have a left-hand thread to deter theft, since they cannot be used in other light fixtures. The term chirality comes from the Greek word for hand, and concerns handedness in many other contexts. Form. The cross-sectional shape of a thread is often called its form a thread form. It may be square, triangular, trapezoidal, or other shapes. The terms form and thread form sometimes refer to all design aspects taken together. Most triangular thread forms are based on an isosceles triangle. These are usually called V-threads of V-threads because of the shape of their letter V. For 60 degrees V-threads, the isosceles triangle is more specifically equilateral. For buttress threads, the triangle is scalene. The theoretical triangle is usually truncated to varying degrees. A V-thread in which there is no truncation is called a sharp V-thread. Truncation occurs for practical reasons. The thread cutting, a thread-forming tool, cannot practically have a perfectly sharp point. At some level of magnification, the point is truncated, even if the truncation is very small. Too small truncation is undesirable anyway, because the cutting or forming tool's edge will break too easily. The part of fastener's thread crests will have burrs upon cutting, and will be too susceptible to additional future burring resulting from dents. The roots and crests of mating male and female threads need clearance to ensure that the sloped sides of the V meet properly despite error in pitch, diameter and dirt and nick-induced burrs. The point of the thread form adds little strength to the thread. Ball screws, whose male-female pairs involve bearing balls in between, show that other variations of form are possible. Roller screws use conventional thread forms but introduce an interesting twist on the theme. Angle. The angle characteristic of the cross-sectional shape is often called the thread angle. For most threads, this is standardized as 60 degrees, but any angle can be used. Lead, pitch, and starts. Lead E, and pitch are closely related concepts. They can be confused because they are the same for most screws. Lead is the distance along the screw's axis that is covered by one complete rotation of the screw. Pitch is the distance from the crest of one thread to the next. Because the vast majority of screw thread forms are single start thread forms, the lead and pitch are the same. Single start means that there is only one ridge wrapped around the cylinder of the screw's body. Each time that the screw's body rotates one turn, it has advanced axially by the width of one ridge. Double start means that there are two ridges wrapped around the cylinder of the screw's body. Each time that the screw's body rotates one turn, it has advanced axially by the width of two ridges. Another way to express this is that lead and pitch are parametrically related, and the parameter that relates them, the number of starts, very often has a value of 1, in which case the relationship becomes equality. In general, lead is equal to pitch times the number of starts, whereas metric threads are usually defined by the pitch, that is, how much distance per thread. Inch-based standards usually use the reverse logic, that is, how many threads occur per a given distance. Thus, inch-based threads are defined in terms of threads per inch. Pitch and TPI describe the same underlying physical property, merely in different terms. When the inch is used as the unit of measurement for pitch, TPI is the reciprocal of pitch and vice versa. For example, a 1/4 - 20 thread has 20 TPI, which means that its pitch is 1/20th inch. As the distance from the crest of one thread to the next, pitch can be compared to the wavelength of a wave. Another wave analogy is that pitch and TPI are inverses of each other in a similar way that period and frequency are inverses of each other. Coarse versus fine. Coarse threads are those with larger pitch, and fine threads are those with smaller pitch. Coarse threads have a larger thread form relative to screw diameter, whereas fine threads have a smaller thread form relative to screw diameter. This distinction is analogous to that between coarse teeth and fine teeth on a saw file, or between coarse grit and fine grit on sandpaper. The common V-thread standards include a coarse pitch and a fine define pitch for each major diameter. For example, 1/2-13 belongs to the UNC series and 1/2-20 belongs to the UNF series. Similarly, ISO 261 M10 nominal outer diameter has a coarse thread version at 1.25 mm pitch and a fine thread version at 1 mm pitch. The term coarse implies here does not mean lower quality, nor does the term fine imply higher quality. The terms, when used in reference to screw thread pitch, have nothing to do with the tolerances used to the amount of craftsmanship, quality, or cost. They simply refer to the size of the threads relative to the screw diameter. Diameters. There are three characteristic diameters of threads: major diameter, minor diameter, and pitch diameter. Industry standards specify minimum and maximum limits for each of these for all recognized thread sizes. The minimum limits for external and the maximum limits for internal thread sizes of the to ensure that threads do not strip at the tensile strength limits for the parent material. The minimum limits for internal and maximum limits for external threads of the to ensure that the threads fit together. Major diameter. The major diameter of threads is the larger of two extreme diameters delimiting the height of the thread profile. As a cross-sectional view is taken in a plane containing the axis of the threads. For a screw, this is its outside diameter. The major diameter of a nut may not be directly measured, but it may be tested with go/no-go gauges. The major diameter of external threads is normally smaller than the major diameter of the internal threads, if the threads are designed to fit together, but this requirement alone does not guarantee that a bolt and a nut of the same pitch would fit together. The same requirement must separately be made for the minor and pitch diameters of the threads. Besides providing for a clearance between the crest of the bolt threads and the root of the nut threads, we must also ensure that the clearances are not so excessive as to cause the fasteners to fail. Minor diameter. The minor diameter is the lower extreme diameter of the thread. Major diameter minus minor diameter divided by 2 equals the height of the thread. The minor diameter of a nut is its inside diameter. The minor diameter of a bolt can be measured with go/no-go gauges or directly with an optical comparator. As shown in the figure at right, threads of equal pitch and angle that have matching minor diameters with differing major and pitch diameters may appear to fit snugly, but only so radially. Threads that have only major diameters matching could also be visualized as not allowing radial movement. The reduced material condition, due to the unused spaces between the threads, must be minimized so as not to overly weaken the fasteners. Pitch diameter. The pitch diameter of a particular thread, internal or external, is the diameter of a cylindrical surface, axially concentric to the thread, which intersects the thread flanks at equidistant points. When viewed in a cross-sectional plane containing the axis of the thread, the distance between these points being exactly 1/2 the pitch distance. Equivalently, a line running parallel to the axis and a distance d2 away from it, the PD line, slices the sharp V form of the thread, having flanks coincident with the flanks of the thread under test at exactly 50% of its height. We have assumed that the flanks have the proper shape, angle, and pitch for the specified thread standard. It is generally unrelated to the major and minor diameters, especially if the crest and root truncations of the sharp V form at these diameters are unknown, everything else being ideal. D2, D, and amp D1 together would fully describe the thread form. Knowledge of PD determines the position of the sharp V thread form, the sides of which coincide with the straight sides of the thread flanks, e.g., the crest of the external thread would truncate these sides a radial displacement d2 away from the position of the PD line, provided that there are moderate non-negative clearances between the root and crest of the opposing threads, and everything else is ideal. If the pitch diameters of a screw and nut are exactly matched, there should be no play at all between the two as assembled, even in the presence of positive root-crest clearances. This is the case when the flanks of the threads come into intimate contact with one another, before the roots and crests do, if at all. However, this ideal condition would in practice only be approximated and would generally require wrench-assisted assembly, possibly causing the galling of the threads. For this reason, some allowance, or minimum difference, between the PDs of the internal and external threads has to generally be provided for, to eliminate the possibility of deviations from the ideal thread form causing interference and to expedite hand assembly up to the length of engagement. Such allowances, or fundamental deviations, as ISO standards call them, are provided for in various degrees in corresponding classes of fit for ranges of thread sizes. At one extreme, no allowance is provided by class, but the maximum PD of the external thread is specified to be the same as the minimum PD of the internal thread, within specified tolerances, ensuring that the two can be assembled, with some looseness of fit still possible due to the margin of tolerance. A class called interference fit may even provide for negative allowances, where the PD of the screw is greater than the PD of the nut by at least the amount of the allowance. The pitch diameter of external threads is measured by various methods. A dedicated type of micrometer, called a thread mic, a pitch mic, which has a V-anvil and a conical spindle tip, contacts the thread flanks for a direct reading. A general-purpose micrometer is used over a set of 3 wires that rest on the thread flanks, and a known constant is subtracted from the reading. This method is called the 3-wire method. Sometimes, grease is used to hold the wires in place, helping the user to juggle the part, mic, and wires into position. An optical comparator may also be used to determine PD graphically. Classes of fit. The way in which male and female fit together, including play and friction, is classified in thread standards. Achieving a certain class of fit requires the ability to work within tolerance ranges for dimension and surface finish. Defining and achieving classes of fit are important for interchangeability. Classes include 1, 2, 3, A and B, and various systems such as H and D limits. Tolerance class is thread limit. Thread limit, a pitch diameter limit, is a standard used for classifying the tolerance of the thread pitch diameter for taps. 4 imperial H or L limits are used, which designate how many units of 0.5 mils over or undersized the pitch diameter is from its basic value, respectively. Thus, a tap designated with an H limit of 3, denoted H3, would have a pitch diameter 0.5 mil times 3 equals 1.5 mil larger than base pitch diameter, and would thus result in cutting an external thread with a looser fit than, say, an H2 tap. Metric uses DA/DO limits, which is the same system as imperial, but uses DA/DO designators for over and undersized respectively, and goes by units of 0.013 millimeters. Generally, taps come in the range of H1 to H5 and rarely L1. Standardization and interchangeability. To achieve a predictably successful mating of male and female threads and assured interchangeability between males and between females, standards for form, size, and finish must exist and be followed. Standardization of threads is discussed below. Thread depth. Screw threads are almost never made perfectly sharp, but instead are truncated, yielding a final thread depth that can be expressed as a fraction of the pitch value. The UTS and ISO standards codify the amount of truncation, including tolerance ranges. A perfectly sharp 60 degrees V thread will have a depth of thread equal to 866 of the pitch. This fact is intrinsic to the geometry of an equilateral triangle, a direct result of the basic trigonometric functions. It is independent of measurement units. However, UTS and ISO threads are not sharp threads. The major and minor diameters delimit truncations on either side of the sharp V, typically about 1/8 of the pitch, although the actual geometry definition has more variables than that. This means that a full UTS or ISO thread has a height of around 65 p. Threads can be truncated a bit more, yielding thread depths of 60% to 75% of the 65p value. For example, a 75% thread sacrifices only a small amount of strength in exchange for a significant reduction in the force required to cut the thread. The result is that tapered wear is reduced, the likelihood of breakage is lessened, and higher cutting speeds can often be employed. Truncation is achieved by using a slightly larger tap drill in the case of female threads, or by slightly reducing the diameter of the threaded area of workpiece in the case of male threads, the latter effectively reducing the thread's major diameter. In the case of female threads, tap drill charts typically specify sizes that will produce an approximate 75% thread. A 60% thread may be appropriate in cases where high tensile loading will not be expected. In both cases, the pitch diameter is not affected. The balancing of truncation versus thread strength is similar to many engineering decisions involving the strength, weight and cost of material, as well as the cost to machine it. Tapered threads are used on fasteners and pipe. A common example of a fastener with a tapered thread is a wood screw. The threaded pipes used in some plumbing installations for the delivery of fluids under pressure have a threaded section that is slightly conical. Examples of the NPT and BSP series. The seal provided by a threaded pipe joint is created when a tapered externally threaded end is tightened into an end with internal threads. Normally a good seal requires the application of a separate sealant in the joint, such as thread seal tape, or a liquid or paste pipe sealant such as pipe dope. However, some threaded pipe joints do not require a separate sealant.